Okay, let's dig into this. Imagine trying to forecast air pollution in a massive city like Shanghai. I mean, over 24 million people live there.
Yeah, it's huge.
You'd think you need just tons and tons of data, right?
Sure.
But here's the really interesting part. Some scientists there built a pretty useful forecasting model using, well, what seems like a surprisingly small amount of data.
That's exactly it. We're looking at the research paper Forecasting Particulate Matter Concentration in Shanghai using a small-scale, long-term data set.
Small scale, but long term. That's the key bit, isn't it?
Right. They used just 4,240 samples, but stretched over 12 years, from 2011 to 2021. That data included daily weather stuff, temperature, humidity, wind, rain from 74 stations.
Okay.
And they also pulled in satellite data, things like aerosol optical depth and the planetary boundary layer height.
Right.
Plus, and this is crucial, they used this special data set called LGHAP. It's China's first high-res, long-term, gap-free air pollutant data set.
Gap-free, how did they manage that?
Well, it cleverly merges satellite info, computer models, and actual ground measurements to fill in any blanks for PM2.5 and PM10. Really smart.
Okay, so the big question for us in this deep dive is, how on earth did they make accurate predictions with what sounds like, relatively little data?
Exactly.
We want to unpack how that long-term view, combined with machine learning, let them forecast pollution a day ahead. It's a great example of making the most of what you have.
It really is.
And I think for you listening, if you ever deal with data constraints, this offers a really useful perspective on what's possible.
Absolutely. Whether you're trying to make forecasts with limited resources, or you're just curious about how air quality prediction works, or maybe how machine learning can be used creatively.
Yeah.
This study has some valuable lessons about getting real insights from the data you actually have available.
Okay, let's start with that small data set idea. Usually for this kind of forecasting, you hear about huge databases, right? Tens of thousands of samples.
Typically, yes.
So what are the main headaches when you've only got, say, around 4,000 data points? Why is that harder?
Well, it's a really good question. The paper points out a couple of big challenges with smaller data sets. First, picking out the real drivers of pollution is tougher.
Like finding the signal in the noise.
Exactly. There's just less data to separate what's truly important from random fluctuations. And any odd bits in your limited data can have a bigger impact on the model.
Okay.
Second, and maybe more critical, is generalization. Your model might get really good at predicting based only on the specific examples it saw.
Like it just memorizes the answers.
Precisely. But then it struggles when it sees new situations it hasn't encountered in that limited training set. It hasn't learned the underlying rules properly.
That makes total sense. You need it to learn the concept, not just the specific test questions. Okay, let's look closer at the data they did use.
Yeah.
You mentioned LGHAP being gap-free. Why was that so important for a long-term study?
Right. The LGHAP dataset is fascinating because of how it stitches everything together. Think about older air quality data. Ground monitoring for PM2.5 really ramped up after 2012 in China.
Okay, so gaps before then.
Potentially, yes, or less coverage. Satellites can help look back further, but they have their own issues, like clouds blocking the view.
Right. Gaps again.
So LGHAP takes multiple satellite measures of aerosol optical depth. That's basically how hazy the air is, and uses machine learning to refine it, even estimating AOD when it's cloudy, using local weather and pollution data. This creates a smooth, consistent record of PM2.5, PM10, and AOD for the whole 12 years across Shanghai.
Wow. Okay, so no patchy data from just one station, but a complete regional picture over time.
Exactly. That consistent baseline is vital for spotting trends and building a reliable forecast model.
So with that solid data foundation, they didn't jump straight into machine learning. They did some statistical analysis first. Let's talk about the seasonal Mann-Kendall test. What did that show?
Oh, yeah. The Mann-Kendall test is neat because it finds trends over time, even if the data isn't perfectly normally distributed, and it can handle some missing bits.
Okay, so what trends popped out?
They found some pretty clear shifts in the monthly averages over the 12 years. Temperature was gradually increasing, and rainfall showed a slight increase too. But on the pollution side, PM10, PM2.5, and aerosol optical depth were all trending downwards.
Interesting. Downward pollution, upward temp, and rain.
And even the planetary boundary layer height, that lowest atmospheric layer, showed a decreasing trend.
What's the story behind those trends? The paper hints at some connections, right?
Yeah, it likely reflects a combination of factors.
Yep.
The decrease in pollutants like PM10 and PM2.5 probably ties into Shanghai's stricter air pollution controls over that period.
Makes sense.
But then reducing those aerosols can actually affect the local climate. Fewer aerosols might mean less sunlight reflected away, potentially contributing to the rising surface temperatures.
Like lifting a bit of a reflective shield.
Sort of, yeah. It's sometimes called a reversal of global dimming on a local scale. And fewer aerosols might also influence cloud formation, possibly linking to that slight increase in rain. The lower boundary layer could also be tied to these atmospheric changes.
It's really all interconnected, isn't it?
Yeah.
Okay, then there was the T-mode, Principal Component Analysis, TPCA. What was that used for?
TPCA is a technique they use to classify the main large-scale weather patterns, the synoptic patterns, over Shanghai.
So like identifying the typical weather setups.
Exactly. They looked at daily sea level pressure and wind fields and grouped them into 7 recurring patterns. And the clever part is linking these patterns to where pollution might be coming from.
Because different weather brings air from different places.
Precisely. Different air masses carry different pollution loads.
Can you give an example? How did a specific pattern relate to pollution?
Sure. They found one pattern, SWP7, involves high pressure north of Shanghai, causing winds to blow from the north. When that pattern happens, Shanghai tends to get higher particle pollution. They think it might be bringing pollution down from Jiangsu province, which is industrial, or maybe even from the industrial Baoshan district within Shanghai itself.
All right.
But then another pattern, SWP1, with winds from the southeast off the sea, usually means cleaner air.
Got it. So understanding the weather patterns gives clues about potential pollution episodes.
Yeah, it adds another layer to the forecast.
Okay, so all that analysis set the stage. Then came the machine learning. They used something called stacked generalization, or SG. What is that, basically?
Okay, think of SG like building a prediction committee. Instead of relying on just one expert model, you train several different ones first.
Like linear regression, random forests, those kinds.
Exactly. Those are your base models. Then you take the predictions made by those models and feed them into another model, a kind of meta model.
Like a manager model.
Yeah, pretty much. This meta model learns how to best combine the strengths of the individual base model predictions to make a final, hopefully more accurate forecast.
Why choose that approach? Especially with less data.
Well, combining different models can make the overall prediction more robust. If one model has a particular weakness, the others might compensate for it. It often leads to better generalization than relying on a single model, which is key with smaller data sets.
Right, pooling knowledge for a better outcome.
Yeah.
Now, given the data limitations, they had to be really careful about what they fed the models, didn't they? Feature selection and engineering.
Absolutely critical. They didn't just dump everything in. First, they did correlation analysis, Pearson correlation, to see which weather variables actually had a decent relationship with PM 2.5 and PM 10.
So they filtered out the less relevant stuff.
Yep. Then they looked at time lags. How much did yesterday's pollution or the day before's affect today's? For PM 2.5, they found the previous 3 days were generally most important.
Okay.
So based on that, they did feature engineering instead of just using the raw pollution values from days 1, 2, and 3 before.
I did what?
They calculated stats like the mean, max, min, and standard deviation of pollution over those 3 days. This creates richer features for the model to learn from without adding tons of new variables.
Smart. Getting more info from the same data.
Exactly. And they scaled everything so no single feature would dominate just because its numbers were bigger.
So a very deliberate process. You mentioned some of the base models, linear regression, random forests, neural networks.
A good mix. They included simpler ones and more complex ones like gradient boosting and k-nearest neighbors too. It was smart to include models known to work okay even without massive data sets.
Right, not just deep learning, which needs tons of data.
Yeah.
And how did they check how well these models actually worked?
They used standard metrics, R-squared, to see how much variation the model explained, root mean squared error, or RMSE, to gauge the average error size, and mean deviation to check for bias, like always predicting too high or too low. And importantly, they used 5-fold cross-validation. That's where you split the data 5 ways, train on 4 parts, test on the 5th, and repeat. It gives a much better sense of how the model will perform on unseen data.
Prevents it from just being good on that one specific test set.
Exactly.
So after all that careful work, how good was the final stacked model at forecasting pollution?
The results were genuinely impressive. For predicting PM 2.5 1 day ahead, the stacked model got an RMSE of just under 12 micrograms per cubic meter. and an R-squared of 0.72.
And how does that compare?
That was notably better than any single base model they tested. And crucially, they pointed out it's comparable to results from other studies that used much, much larger data sets.
Wow. So they matched the performance with less data.
Pretty much, yeah. And importantly, the model was pretty good at catching most of the major pollution peaks, like some events in January 2019 and November 2020. That makes it practically useful for warnings.
That is remarkable. Were there any downsides? Any areas where it struggled?
Yes, they were upfront about limitations. It found it harder to accurately predict the really extreme pollution events, the very highest peaks.
Okay, the outliers are always tough.
Right. And they also noticed it tended to slightly overestimate PM2.5 when the actual pollution levels were low. They think that might be because the model didn't fully capture the ongoing strength of that long-term downward trend in PM2.5 we talked about earlier.
Interesting. So still some fine-tuning needed, especially for extremes and low levels. But overall, what's the big takeaway here? Why is the study so significant?
I think there are a few key things. First, it's proof that you can do valuable air quality forecasting without needing absolutely enormous data sets.
If you're smart about it.
Exactly. If you leverage long-term data, understand weather influences, use sophisticated ML techniques like stacking, and do careful feature engineering. Second, it really highlights that link between air quality actions and climate effects.
The temperature and rain changes alongside pollution drops.
Yeah, it shows you need strategies that think about both together. And finally, from a practical view, this kind of forecasting, even if not perfect, can be a huge help for public health alerts and guiding policy, especially maybe in places that don't have super dense monitoring networks yet.
So the real insight is that the quality and the time span of data, plus clever analysis, can be just as powerful, maybe even more powerful sometimes, than just raw quantity.
That's a great way to put it. It's not just about big data, it's about smart data.
That really is an aha
Oh,
moment. It's about intelligent use of what you have.
Precisely. And that leaves us with a final thought for you listening. If this approach worked for air pollution forecasting in Shanghai with their specific data set, where else could it work? Think about other areas, maybe in ecology or social sciences or resource management, where you might have long-term records but not massive data sets. Could similar smart techniques unlock insights there? What localized solutions to big challenges could we find by looking at the data we do have, just maybe through a different lens?